Hi everyone, today I want to prove Euler's formula where e to the imaginary x equals sine x times the imaginary number I plus cosine of x. So today I'm going to prove this to you using the Taylor series. If you remember the Taylor series, usually you were just given these or maybe you had to derive them by hand. Basically we're going to use the idea of this series, right? We're going to make this a series on one side and we're going to make it equal these series on the other side. We're going to see that we can group terms and make some simple approximations using these Taylor series. So let's get into it. I also want to point out a trend when we look at imaginary numbers. This will become important. I just want to point out here. Imaginary number I is going to be equal to imaginary number I, but if we square it, it's -1 because we define this to be square root of -1. Well, you multiply two square roots together, the radical goes away, it's just going to be -1. And then -1 times I is going to be -I, right? And then multiply that by I again, we're going to get 1. So hopefully you can follow that. I won't go into too much detail further than that, but if you can rationalize it, I pray that you do. I hope you see the pattern. So we have this, we laid the groundwork of the idea. Now let's go ahead and do it. So we're going to say that e to the x is equal to this here, but we're going to add the imaginary part in. So all we have to do is multiply every term by I to some increasing power of n, which would be the exponent. So this is going to follow, the general formula would be the sum of, and instead of talking about theta, let's talk about x. X to the n, I to the n, over n factorial, where we start at n equals 0 and we go to infinity. So let me just make sure I have that right. So that 0, 0, okay, and then yep, over n factorial, that looks right. Theta, so yep, we have x. Okay, so when we have this imaginary unit in here, we just add this little I term to the n that we can kind of multiply through. So instead of this, right, we're going to imagine this but with an I. So it's going to look like this. It's going to go I, and then it's going to, or sorry, I should say it's going to go 1 plus I x plus I squared x squared over 2 factorial. This would technically be over 1 factorial. This would be over 0 factorial. Okay. Plus I to the third x to the third over 3 factorial. And it would go on and on and on and on and on. But actually for this example, we're gonna go really far out so we can see this pattern. Plus I fourth x to the fourth over 4 factorial plus, and we'll just go to the 5th term, that's okay, over 5 factorial. So I want to make some simplifications here, which is going to help us see some things. We're going to use this identity or this set of values where I is equal to I, and then so on and so on and so on. So let's go through it. So I squared is just we're going to simplify to -1. So we're just going to add a minus sign here. I'm going to kind of shorten these so I can shove it in there. We're going to simplify this to -1 because we said I squared is -1. For I to the third, we're just going to add a minus sign out here. X to the fourth, we're just going to call 1. And then I to the 5th is going to repeat. So this just becomes I. And in this case, we're just going to keep it I to the 5th. So hopefully you follow kind of what's going on here. But now we're going to group some terms because then we're going to start to see a pattern. Okay, so I am going to group every even term including this one here, the 1, with the other guys. So e to the xi is equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. And this is going to continue until we get to x to the 2n over 2n factorial, right? Yeah, we'll go with that. I think that works to kind of get the point across. Plus, it would be plus or minus, right? You don't really know which one it would be. And then we're going to add this to a separate series, and we're going to take the odd terms now. So we're going to say I x over 1 factorial minus I to the 3rd x to the 3rd over 3 factorial. And sorry, I made a mistake. I made a mistake here. We need to drop the 3rd in the 5th because it's just gonna alternate like this between I and negative I. So we're gonna drop the 3rds and stuff, and we're just gonna call it I. So I x to the 5th over 5 factorial. So I hope that you're able to see the general pattern. We have e to the ix, right, is equal to this Taylor series because we took a generic Taylor series of the e to the some variable theta function, and we added the I in there, and it made this whole thing. And one more thing I want to add over here, this would be plus or minus the n term dot 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 is going to be x 2n plus 1. So if we start at 0, right, so 2n x plus 1 over n 2n plus 1 quantity factorial. So I just wanted to make that distinction because it doesn't end at that term. It keeps going on till infinity. So we can kind of see two unique sets of terms. One is following this even pattern where it's going 1 negative x squared over 2 factorial, right? It follows a unique pattern of that, right? Whereas these terms starting at n equals 0 follows this kind of pattern, right? They're two different series. Now, when we look at cosine and sine, just generic Taylor series, we're going to notice that they kind of follow the same pattern where, this first group of terms kind of looks like the cosine, right? We have 1 minus some variable of x squared over 2 factorial. And then it's added to x to the 4th over 4 factorial. It turns out that this perfectly is a cosine Taylor series. And because they're both approximations, and the approximations are technically exact, even though they're not finite in how long you can make that Taylor series approximation, we're going to call this cosine of x. Right? So e to the imaginary variable ix is equal to cosine x plus the rest of this junk over here. Okay? It's important now to look at that and kind of distinguish what's happening. So to make things a little bit easier to see, and I also want to add that this is I to the, or just I should say. So we can factor out an I here. We'll factor out an I out of this because every term has an I in some capacity. And what we're going to notice is the pattern x minus x to the 3rd over 3 factorial plus x to the 5th over 5 factorial plus or minus dot 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 x to the 2n plus 1 over 2n plus 1 quantity factorial. Okay, so all I did was factor out the I. Now I want you to take a look at the Taylor series that I have up here, or just any Taylor series of sine of a variable x. In this case, I use theta. We're going to notice it follows the exact same pattern this Taylor series does. So all we're going to do is call all of that junk sine. So when we look at it, e to the ix equals cosine of x plus the imaginary number I, because we factored it out, and it's a product of this times this, and we'll call this sine of x. Okay, so hopefully you were able, through the Taylor series definitions of e to the x, right? We kind of elaborated what this is saying, e to the xi, and we expanded with Taylor series, different components of this, right? And we grouped it together, and we found that e to the ix is really equal to two components of this sum, which we can just simplify to be cosine plus I sine x. So hopefully it wasn't too hard to follow what I was saying. It's kind of really nice math that occurs here. But that's going to be all for this video, guys. If you guys did enjoy, please like, subscribe, and comment if you have any questions. But other than that, have a wonderful day. Bye-bye.